Okay, so let's start our lecture today. Uh, so yeah. So let's continue with the sigma function. After the sigma function, so uh, uh, there is also another relation that this sigma function satisfies. So that's uh, yeah. Okay, so uh, uh, so so we have sigma z is entire, which we have just showed, and also satisfies the relation that sigma prime z over sigma z, which is equal to zeta z. Okay, so so let's see whether this let's verify this one. So okay, so let's recall what is this zeta z. So so this zeta z by definition, so this is equal to 1 over z plus sum of omega not equal to 0 over the summand as 1 over z minus omega plus 1 over omega plus z over omega squared. Okay, so okay, so let's check the so first we want to figure out what is this sigma prime z, right? So let's try to figure out okay, so the question is that what is sigma prime z? So okay. Okay, so okay, so let's first fix Okay, so in order to show this relation, let's first fix any point z. Okay, so okay, so fix let's say z naught. Okay, so let me get this verification. So let's first fix the z naught, because this zeta function is basically undefined at 0 and z at the lattice point, right? So what we do is that we want to say z is c take away the all the lattice point including 0, right? So this is the notation for the lattice point including 0. So okay, so and then okay, so then the question is that okay, so what is sigma prime of z naught, right? So what is the question is that what is exactly sigma prime at z naught? Okay, so remember that the way we define sigma z is that it's being defined originally by any compact subset of C, right? So yes, so and then by the sigma kz, right? So okay, so let's do this one. So so first we fix, because what I'm worrying is that okay, yeah. So what I'm a little bit worried is that so this k, because I want to use the argument about taking the derivative of sigma kz, right? So so this k, so so I can't take arbitrary k, because arbitrary compact set, there might be an issue that the compact set may be like just a like closed interval where we cannot really like formally see the derivative on this compact set k. So what I do is that so we fix k to be equal to a closed disk, right? Okay. So this R is probably different from this R. So where R is equal to modulus of z naught plus some number, let's say +1. Okay. A closed disk that contains this point z naught. Okay. So now so by the argument by the argument that we just did here, right? So so I need to take the derivative, okay. So then so choose this sigma k as we did earlier, okay. So namely yeah, namely for this compact set, right? So we know that there exists a unknown such that, yeah, so as we did earlier, like the process we did earlier, right? Because this k is arbitrary, so because k is arbitrary, so we can define because k is arbitrary. Yeah, because k is arbitrary, we can define this sigma kz using the mechanism that we did before. Okay, so yeah, as we did earlier, okay, so maybe let's do this. So so fix sigma k such that this sigma z is equal to sigma kz. Okay. For z in k. Okay. 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 So and then let's see. So okay. So then we have that sigma k of z naught, which is equal to okay. Yeah. So yeah, so what we do is that because this sigma z is being defined as any it's defined based on complex set, right? So basically for each complex set we define and also for each complex set and for each z value on the complex set we define the sigma z based on the sigma kz, where sigma kz is being defined on the complex set. So yeah, so we just pick this function to be the generating function, like the original defining function for this sigma z. Okay, so by the definition of sigma k, okay, so we have that, so this is equal to z times the product j from 1 to n naught of so this is the final product 1 minus z over omega j times e to the, so now this is sorry, this is z naught. Oh shoot, I think I need to do it without z naught because I need to take the derivative first. Okay, so e to the z over omega j plus 1/2 z over omega j squared. Okay, so and then times e to the times e to the L of n naught of z. Okay. So this is equal to, okay, so now we take the derivative, right? So let's see. So now sigma prime k at z. Okay, so so what happens if we take the derivative of this guy? Okay, so there should be many product rule, right? So okay, so maybe let's say k equal to so for z in this k interior, okay, because let's be strict. Okay, so okay, so let's apply the product rule. So first I take the dt of z, which is 1, right? So we get the product of 1 minus z over omega j times z over omega j plus 1/2 z over omega j squared times e to the l naught z. Okay. Okay. So now plus. Okay. So I think I'm free to erase this one. So okay, so now we want to take the derivative of the left hand side of this whole thing, right? So so the derivative of this whole thing is equal to what? Okay, so let's do a few steps. So the derivative of this guy. So so basically 1/2 z over omega j squared times e to the l and not z. So okay, so okay, so here there is so if we think of, because okay, so think of this as like so this one is like a whole, right? So this one is like one thing. Okay, and then here there is like n things being multiplied together, right? So here there is a total like n plus 1 product, and then when I take the derivative, right? So first I take the first one and then the rest the same, and then I keep the first one and then I take the derivative of the rest, and then for the derivative of the rest, yeah. So okay, so let me just write. Let's denote it at the star. Okay. So star is equal to so first I take the derivative of the first one, which is okay, so which is 1 minus 1 over omega j times e to the z over omega j plus 1/2 z over omega j squared. So and then plus, okay, so plus so this is the polar rule, right? So 1 minus z over omega j. Shoot, this should be 1, okay, so because I'm taking the derivative of the first term. Okay, so 1, and then the derivative of the exponential part, right? Okay, so the derivative of the exponential part is e to the z over omega 1 plus the same thing, 1/2 times z over omega 1 squared times the derivative inside. Okay, so what is the derivative inside? So this is equal to 1 over omega 1 plus, so this is the chain rule again, right? So so this is z over omega 1, right? So and then times the derivative inside, which is 1 over omega 1, so which is omega squared, okay. And then okay, so this is the derivative of the first thing, okay. So times the product j from 2 to n naught of this guy 1 minus z over omega j times e to the z over omega j plus 1/2 z over omega j squared times e to the L of n naught z. Okay. And then plus. So now okay, so now what's left is just it should be the first term, right? So keeping the first term the same, which is 1 minus z over omega j e to the z over omega j plus 1/2 z over omega j. Shoot, the first term is omega equal to 1. Okay, so omega 1 z over omega 1 squared. So this is the first term, and then times the derivative of the rest. Okay, so okay, so I think maybe it's better for me to do this. So because this is like a consecutive formula of the derivative of let's say many variables using product rule, right? So I think so if you have let's say the derivative of let's say f1 times f2 times times fn, right? So yeah, I think there should be a general formula about the product rule using like n n things being multiplied together. So I think I can use the induction to prove this formula. So so what is the formula that I want to say? So we know that the ddz of f1 times f2, right? So which is equal to f1 prime of f2 plus f1 times f2 prime, right? So let's see. So let's see for three variables. So if we have the ddz of f1 times f2 times f3, so which is equal to f1 prime times f2 times f3, right? Take the detail of first one, keep the rest the same, and then plus keep f1, and then taking the derivative of the rest, which is I think it's like f2 prime times f3 plus f1 times f2 times f3 prime, right? Yeah, so I think so there are these patterns. So let's say so assume this pattern holds for n minus 1. Okay, so now let's say for like fn times times fn, so this is equal to so f1 prime times f2 times times fn, right? So this is the first part, and then this is and then times keep f1, and then times the derivative of f2 times times fn. Okay, so then by we can use the inductive assumption for this guy. So and so this is equal to so by the inductive assumption, so we have so let's mark it as, let's mark the whole thing, okay, as star. Okay, so did I use star? Okay, star with a column. Okay, so star column, which is equal to so f1 prime f2 fn plus f1 times so this is f2 prime, right? f3 fn. Oh, okay, so f2 fn. Okay, and then this is equal to plus f2 times f3 prime fn So plus f plus plus f2 times f3 times all the way fn prime. Okay, so square bracket. Okay, so this is equal to f1 prime f2 fn plus f1 f2 prime fn. Okay. f1 f2 f3 prime fn plus f1 f2 f3 fn prime. Okay, so this holds. Okay, so yeah, I'm just expanding this function here. So okay, so okay, so we can use this one, right? Use this one for here, right? So so okay, so okay, so okay, so I'll erase this one, okay, because I need the space for the formula here. So yeah, so I'll use this formula for this product here. So okay, so let's say using product rule, multi-version product rule. Okay. Okay, so we have so basically the duty of the second one basically is exactly the same as the first one, right? But just substituting omega 2 in place of this omega 1. So this is equal to, let's see, so this is equal to 1 minus 1 over omega 2 e to the z over omega 2 plus 1 half z over omega 2 squared plus 1 over z over omega 2 z e to the z over omega 2 plus 1 half z over omega 2 squared times 1 over omega 2 plus z over omega 2 squared. So times the product. Okay, so j from 3 to n naught of 1 minus z over omega j e to the z over omega j plus 1 half z over omega j squared times tau. Okay, so this is like the second term is being taken derivative. So and then okay, so and then the very last part should be the product j from 1 to n naught, right? Of 1 minus z over omega j e to the z over omega j plus 1 half z over omega j squared, and then the derivative of the last one, which is times e to the L of n naught z times L n naught prime z. Okay, so this whole thing is sigma prime kz, right? Okay, so now we take the fraction. Okay, so now we have so this implies that so sigma k prime z over sigma z. Okay. So this is equal to the fraction, right? So sigma kz is like z times all the products here, right? So okay, so here there are many terms for the sigma prime z, right? So maybe we can express the sigma prime z as a finite sum of these terms, and then take the division term by term. Okay. Okay. So I think I'm probably running out of time today, so I'll do the computation next time.